Hi, I wanted to do a walkthrough of that exercise that we started on Friday with relativity, both relativistic uh, velocity additions as well as um, some relativistic momentum for that second problem. So for the first problem on this exercise, we have these two cars. This one is number 1, moving at speed v1. Gosh, V1 is 0.4 c. That's, of course, as observed by some observer in a rest frame. Observing this one, there's a person in here, and I'm going to call this the S double prime frame. Would be the frame at which this car number 1 is at rest. There's also car number 2 that the observer at rest over here observes at V2 equals 0.6 c, and they're both moving in the positive I hat direction. And there's a little guy in this frame of reference that I'll call S prime. Okay, so I want to know how fast does the observer in car number 1 see car number 2 traveling. Now, car 2 is moving faster but in the same direction than car number 1. So Galileo would just say something like the difference between these velocities, and this person would see this car move at 0.2 c away from him, from the S double prime observer. And we know that's not going to be exactly how this works. So we instead have to use our velocity transformations and say something like, here, let me be careful here. So the ux, I'm going to call the primed frame, I'm going to label it double prime, will be, let's see, ux minus v. This v is the relative motion between the coordinate system I made the measurement in here and the frame that I'm going to. I'm transforming into this frame, so this is actually v1, and divided by minus 1, or 1 minus ux v1 over c squared. So this is just writing out that velocity transformation from the unprimed frame to the primed frame, in this case double primed frame. And this ux, that's the velocity of the thing I'm interested in as measured by the unprimed observer, and that is the car number 2's velocity. So ux here is actually v2. So I'll rewrite this again as v2 minus v1 over 1 minus ux, or sorry, this is the ux is the v2, so this is v2 v1 over c squared. And just like we would expect, if v over c was a very, very small number, then this, the velocity, which is actually u double prime 2, we're measuring the speed of this car in the double primed frame, is just the difference of the velocities over this factor. And when v over c is very small, it would just be the difference of the velocities, or 0.2, which is what we expected Galileo would have said. So in this case, it instead is 0.2 c divided by 1 minus 0.4 times 0.6, where those c's will have already canceled out in the denominator. There's a c here and a c here, canceling both of those. And so I'm just actually going to then plug this thing in. We'll get in the denominator 1 minus 0.4 times 0.6 is, so we got 0.2 c is 0.76. And then if we do 0.2 divided by 0.76, we get 0.26, and then the c is still there. So instead of 0.2 c, the S double prime observer sees this car number 2 moving at 0.26 c away from them. Okay, so then we can say that this person here is also going to throw some ball back with a ux prime velocity, just directly backwards off of the car, and then this ball is going to be caught by the observer in car number 1, and we're going to kind of see what happens from the outside perspective, from the unprimed frame perspective. So how fast does this ball move in the unprimed frame? So we would have to then write our inverse transformation of this and say ux equals ux prime plus v. This is the difference between these velocity here, so this is v2. The difference between the unprimed frame and the single primed frame. Then we got 1 minus ux prime v2 over c squared. To remember which velocity this v represents, just think about what 2 frames are you considering at that moment. So I'm considering velocities as measured in the primed frame. That's how I know that this ux prime is minus 0.6 c in the I hat direction. He's throwing it backwards with this velocity relative to him. And so we have that one velocity measured in the primed frame, and we also need to consider the velocity between the 2 frames we're considering. And I'm thinking about how does this person see it, so I'm talking about the relative motion between these 2 frames. And so then I can just plug in these numbers. I've got minus 0.6 c plus 0.6 c in the numerator, and then 1 minus 0.6 times 0.6 in the denominator. Of course, the numerator is 0. So this observer would see that ball come to a complete rest, just like kind of that Mythbusters video we talked about, where the car is going back this way and we shoot it off in this direction. That remains unchanged, even in relativity, because now that ball will just come to a complete rest as observed by this person. Now, of course, this person will not see that same ball at rest. So we could then think about what is the velocity of the ball in the double primed frame. And to do this, we have to then think, okay, now I want to know from the perspective of this person. So I'm going into the double primed frame, and we're going to consider from this being the rest perspective. So now this will be a little confusing because I've got a primed frame and a double primed frame, but remember, no frame is special. So I'm going to write out this equation as though I'm transforming from this frame to this frame. So this is going to be the velocity in the initial frame of reference plus the relative motion between these 2 frames, which we calculated earlier as 0.26 c. This is effectively v2 as seen by this frame of reference. So I'm going to put this v2 double prime and 1 over u prime v2 double prime over c squared. Sorry, this is a plus, not a minus, because we've got pluses. Okay. Then we're just going to plug in things, because we know u prime, as seen here, was minus 0.6 c. And then v2 double prime we calculated in the first part is plus 0.26 c. All of that over 1. This would be a plus, but it's actually going to be a minus because of this minus sign from here. So I'm going to just write this as 1 minus 0.6 times 0.26. So this minus sign flips this to a minus here. And if I plug all those numbers in, I'm going to get something like 0.4 c is how fast this ball appears to approach this car. Now, of course, we could have probably figured that out just from intuition alone, because this ball appeared from this observer to be at rest. And this observer sees this car move towards the ball at 0.4 c. And sorry, I forgot there's a minus sign here. So the ball from the observer, from this S double prime observer's perspective, approaches it at 0.5 or 0.4 c as well. So that checks out with kind of some intuition. Okay, then so that was part B there. Part C, if the S frame observer sees the ball being thrown while the cars themselves are some delta x apart from each other, where delta x is 10 to the 8 meters apart, how long does the ball move before being caught by the observer in the S double prime system? So all we have to do here is just think delta t is going to be delta x over the relative velocity, which the unprimed observer sees that distance, and we see the ball at rest and the car racing towards the ball at 0.4 c. So this is just v1, and this is 10 to the 8 over 0.4 c. And if we plug those numbers in, we're going to get about 0.83 seconds. So the unprimed observer sees the ball being caught 0.83 seconds after being thrown. The last thing we can think about is how long does this take from the perspective of the observer in S double prime, the person who's going to catch the ball. Sorry, I keep losing my drawing off the top here. So how long does this take? Well, that's going to be delta t double prime will be the distance over, now we saw that the ball races towards the double primed observer at 0.4 c as well, so we'll put 0.4 c down here, but this distance is going to be length contracted from this person's perspective, and so this is delta x over gamma over 0.4 c. And that gamma here, we can real quick just do a 1 over square root of 1 minus 0.4 squared gives about 1.1 approximately. We plug that in here, delta x then becomes something like 9.1 times 10 to the 7 meters over 0.4 c, or about 0.76 seconds. So a little bit less time happens. Of course, we could have done this a slightly different way and say we also know that the time is dilated, so we can just take the total amount of time observed by the unprimed observer and divide that by gamma, and we'll get 0.83 divided by 1.1 is again 0.76 seconds. So we can get the answer either one of those two ways. Okay. So that's all of this velocity addition problem. Always just try to kind of write out these two transformations when you're doing one of these. Again, I'll write them out. 1 plus ux v over c squared. And then the inverse transform is easy to get to by just flipping the primes and unprimed things and flipping the sign of v. So that's where I forgot to do that just then. 1 minus ux v over c squared. So we have these two transformations. Just remember, what do each one of these velocities mean? So the velocity when measured at rest is the unprimed velocity. The primed one is the velocity that would be measured in a different frame. If you were an observer in that frame, moving in that system at rest with respect to that coordinate, this is what you would see, but we would see it move at a different velocity because there's a relative motion v between the two coordinate systems. So try to conceptualize what all of those velocities are to use these formulas correctly. Okay, now I want to go and do the backside, a momentum problem. And this is going to look very similar to the momentum problems that you probably did in your first semester physics course. I'm going to have one big massive particle with total mass m, capital M, and that particle is going to decay and break into three pieces that all have some little m naught, some rest mass, and they're all three particles that are breaking out of this thing all have the same total mass, small m. Now the one that's recoiling to the left moves at 4/5 the speed of light, straight down the minus I hat axis. The particle going down moves at 3/5 c, sorry. And that's going in this minus j hat direction. And we want to figure out what is u and what is theta. So we have to conserve momentum to figure this out. Now, we figured out that the momentum is now gamma m u instead of just m times u. And so we can conserve momentum in the x direction and say that if we add up all the momentum in the x direction, that better be equal to 0 because this particle, capital M, was initially at rest in this coordinate system. And the same thing will be true in the y direction. So let's start writing these things out. I'm going to call this particle here particle 1. This one here will be particle 2, and this one here will be particle 3, just so I can denote them. So in the x direction, we've got particle 1 carrying all this momentum away to the left. That has to be balanced by a component of the momentum here from particle 3. So this is going to be minus, because it's going in the minus x direction, gamma 1 m times u, which is 4/5 c. And then we'll add to that gamma 3. Sorry, wait for that 1 second. Okay, I answered the door, and the dog has calmed down. Okay, where were we? We were writing out the x momentum here. So this particle 3 has some total momentum gamma 3 m u, but we only want the piece of that that's along the x dimension, so that's going to be cosine theta. So that now gives us a relationship that has u and theta, the things that we want to find, and a bunch of things we know in terms of gamma 1 we can calculate, and c, all of these things. We're going to cancel out these m's because we can just divide everything by m, and there. Okay, so we've got some piece of this. We'll also need the y equation. So we'll have here minus gamma 2. I'll put this as minus because it's in the minus j hat direction. M times 3/5 c. And that will be balanced by some amount of momentum, gamma 3 m u, but now sine theta to give us the vertical component. Okay, so again we can cancel the m's. I'm going to bring the x equation down here, and I guess first let's solve for gamma 1 is 1 over the square root 1 minus 4/5 squared. If you track all this through, this goes to 1 over the square root of 1 minus 16 25ths, which is 1 over square root of 9 25ths, which is 1 over 3/5 or 5/3. So there we go. We've got gamma 1. We can also do the same thing with gamma 2. And we get 1 over the square root of 1 minus 3/5. And for the same reasons, we would get 9/25. So then we get 1 over square root of 16/25. This is going to be 4/3. Wait, no, that's not correct. We're going to get 5/4. There we go. The 3 here becomes a 4 for this one. Okay, so now let me do the x equation again. Let's put it down here. We have gamma 1, which is 5/3 times 4/5 c is equal to gamma 3, which we don't know, but I'll write it at times u. So I'll say u times gamma 3 would be u over square root of 1 minus u squared over c squared times a cosine theta thing. And on this left-hand side, we can cancel the 5's, and we just get 4/3 c. I'm actually going to multiply both sides by this square root factor down there. 1 minus u squared over c squared is u cosine theta. And now I want to square both sides of this equation, because I don't want to deal with this square root. So we have 16c squared over 9, and I'll actually distribute out this whole square root. So this would be 1 minus u squared over c squared without the square root then. I'm going to take this 16c squared over 9, distribute it through, so this is 16c squared over 9 minus 16u squared over 9, because the c squared here will cancel that c squared, and we'll pick up the u squared. And that is then u squared cosine squared theta. Finally, just, let's see here. I'm gonna leave it like this for now and go to the other equation. So this was the x equation. Let's go to the y equation here, and we'll do something similar where we have gamma 2, which is 5/4 times 3/5 c is equal to gamma 3 u sine theta. So we're going to again do u over square root of 1 minus u squared over c squared sine theta. We'll do all the same steps again, cancel the 5's. 3/4 c 1 minus u squared over c squared equals u sine theta. This would be square rooted unless I did this where I square everything. So I'll make this 9/16 c squared is u squared sine theta squared. Hopefully doing a couple of those steps at once is not too bad. And I guess we can do the same thing, distribute this through again. There. So we get back to the same kind of step. And one nice property, and maybe you recognize this already, is if we add these two equations together, we know sine squared plus cosine squared is 1. So this is the trick to this one. I'm going to add this to this, and then this to this, so I can just add these two equations together. And I will get u squared, so I'll write the right-hand side now on the left-hand side. Sine squared theta plus cosine squared theta, which is, of course, this is just 1, and that will be equal to 16/9 c squared minus 16 u squared over 9 plus 9/16 c squared minus 9/16 u squared, like that. Okay, so now, okay, sorry, I need to make sure everything is all good still. This is u squared, and then I'm going to bring my other terms that have u squareds in them to this side as well. I'm going to have 1 plus 16/9 plus 9/16, and that will be, this whole thing went to 1. That will just be equal to 16 over 9 plus 9 over 16 c squared. Now, if I add all of these things up, let's see here, this becomes about 3.34 and 2.34. So I can then just say u squared is c squared in the ratio 2.34 to 3.34. And if I square root all of that, I will get, or square root of that, 2.34 over 3.34 c squared. That will be about 0.837 c. So that's the speed of this thing. Lastly, we would say, okay, what's the angle? We just have to return to, say, one of these equations. So let's take this one and say we know 3/4 c is equal to, oh wait, no, sorry. The way I wrote this out, I actually used the x equation, which is 4/3 c is equal to u cosine theta over square root 1 minus u squared over c squared. We now know u, so I can plug in my numbers here, and this becomes, my gamma factor is about 1.827 times u, which is 0.837 cosine theta, and that's about equal to 4/3. So since I canceled the c here with the c here, and if we put all this on one side, cosine theta is approximately 0.8716 then. And then in doing cosine inverse, we would get about 0.512 radians, or convert that to degrees, which is about 29.4 degrees. So once we have these equations set up, all the rest of this is just similar algebra to what you've done before with momentum conservation equations. We just have to change our definition of the momentum and remember how to calculate things like gamma, but everything else is simple algebra. So we now know this is moving about 30 degrees up from the horizontal, and it's moving at about 0.84 c. Okay.